Okay, so we said the history of computing extend beyond electronics to devices like the abacus. According to your unit two, let me go in there. Yes, according to your unit two, talk about things of 1805, like using the abacus, the Jacquard loom, analytical engine. All these things are in the 19th century. You can see 1805, you can see 1834. All these are in the 19th century. Okay, and um, in the first early pioneers of computing, it also talks about using these old machines, so using these old things. Let's just say the main point of the pre-electronic computing was the analog versus the digital computing. That was just the main point, the analog versus the digital computing. And digital actually is dominating due to their scalability. They're dominating almost everywhere. So the focus on of modern computer history is mainly categorized into that digital aspect or that electronic aspect. It's mainly categorized into that. So um, now the six generations of computers. The first generation around 1937 to 1953, core technology, vacuum tubes. Now, vacuum tubes were the electronic switches. Do you know how big those things were? They were, okay, let's just say one room. A small one room, not so large like that, but those computer heads were very large. And nowadays, you see your computer, you see the CPU, everything is integrated. You see the motherboard. As of that time, they use valves. Like, let's say you are passing pipe from one place to another. That's what they're using to do their own connections for the system. Okay, if water should touch that thing, you and the system will fry together. You know, that's how big those systems were, right? So vacuum tubes, electronic switches, okay, they were faster than the normal electromechanical relays, but they were not comparable. Okay, they were kind of comparable in reliability, but the vacuum tubes were faster. Now the other one they were using was electromechanical relays, and I'm going to explain that. Those electromechanical relays use what you call magnetic energy, electrical magnetic energy, as if you're trying to recreate a turbine, or at least as if you're trying to recreate another connection. And that's a lot of work, that's a lot of space, that's a lot of heat. And you can't tell me that as a human being, they were very uncomfortable operating such things. They were very uncomfortable operating it because it's kind of generating heat. It's generating so much heat. So it made them very uncomfortable. All right. All right. So talking about the early electronic calculator, that's the one for by Atanasov under the 19 this was around the 1937 to 1953. This is the first generation. We have the ABC. They call it the Antenna Berry computer. ABC. It came out in your TMA, so please take note of that one. Antenna Berry computer. ABC. 1937 to 1941. Early electronic calculator, but not programmable. What does that mean? That means that these calculators were able to do things addition, subtraction, yeah, addition and subtraction mainly, and but they were not being able to be programmed. That means they were not put into systems like the calculators we have now. They were not being put into systems. They were just there, just like your abacus, just like you using mechanical things, all right? But it was just more faster using the vacuum tubes. So you could not program anything. Everything was kind of manual. If you want to press two, you press two, and and you wait for the two to load. And there are lots of things that you calculate with your head. Let's say you're trying to calculate a differential equation, and in your differentiation, you're kind of wanting to just put in the system. Now, calculators are programmed to solve differential equations. You just put in your differential equations and boom, the calculator will solve it for you. You get. Then, probably the only thing you will get with the Atanasoff Berry computer is the plus and the minus, or probably, let's say, the multiplication. That's all. It's limited. So the remaining things you'll be using your brain to add, do one or two together. Now calculators have made us lazy, you know. I still see some students struggle with calculator though, and they're struggling to use their brain. And a student has told me that before that, but sir, the calculator was created for us to use, you know, so that we don't have to pass through all the stress. It's a good machine. And actually, the student is right. So it's a good machine. It has been programmed to make work easy. But it's just that we give computer too much power, we might lose our human dignity. All right, so yes, Colossus. We might not be able to think properly. Colossus. Colossus 1943. Now, if I tell you about the ABC computer, you know it is around the 1937 to 1941. That's for the ABC computer. So if I say ABC computer, what does it mean? What's the full meaning? Atanasoff Berry computer. This was for early electronic calculator, but not programmable. Okay, so that's the Atanasoff Berry computer, ABC. So just because recall, because I'm going to say ABC, and you should be able to answer me. And then we have Colossus. Colossus 1943, designed by Turing. There is an organization I was trying to work for. Was it last year? It was Turing that was hosting it. Turing is now his foundation, and we're hosting lots of scientists, mathematics to come into the program. So Alan Turing, um, this Colossus machine was used to break down codes during the World War II. All right. So, and how were they able to use this to break down code? This was around the part during the World War II was where they used to break down radio signals. Um, that's how the Americans defeated, you know, a lot because even the British military defeated a lot. Being able to break down signals from various places. That's what Alan Turing's Colossus did. Colossus is 1943. For what? Breaking codes. When did they use it? World War II. All right, or the Second World War. Um, it's also called the Turing machine. Then we talked about, I know we talked about these things. My brain is just telling me we talked about. So ENIAC, that's the Electronic Numerical Integrator and Computer, around 1945. The first general programmable electronic computer controlled by external switches. No. So have you seen the first one from vacuum tubes is now evolving. So when it got to ENIAC around the 1945, from the 1937, after Turing's Colossus machine, around the 1945, 2 years later, they were able to bring about the first programmable electronic computer. And this time around, it was controlled by external switches. All right, external switches, but it was limiting the speed. Let's just put it this way: external switches are still almost like vacuum tubes. They are still vacuum tubes. Then EDVAC was like our memory where we store data. And remember, I told you guys there was one picture of the first, how many was it, 5 kilobyte or 2 kilobyte memory? This thing looked like a box, like they were pushing it together. Memory card now that you see that is very tiny. That's the work of integration. This thing looked like a box, like they were literally pushing it together. People were holding it and pushing it together. And to them, it was a wonderful discovery. You know, had they been there alive now, they'll be like, ah, man, look at what we created. And you know what, two kilobytes we store right now in our present age? You can't even use that one for data. You can't use that one for even data self. That's what 2 kilobytes will store. All right. So it was very big. That was the ENIAC. And then we had the EDVAC. So EDVAC introduced the critical concepts of stored program. That's EDVAC. Then I told you guys about the UNIVAC, the first commercially successful computer, and this was 1952. Okay, 1952. This was the first commercially successful computer, the one that had the normal monitor and the normal keyboard and the likes like that. Okay, so 1952. I remember growing up, um, my mom then would tell us that they used the system. Not everyone actually had system at home, but they were opportune to be trained because she worked with Nigeria Airways, so she was opportune to be trained using the system. She said they'll tell you that the keyboards don't bite. Then they were just getting used to it. They were getting introduced to it. So the first commercially successful computer with a big-headed, remember those monitors that look like now most of the monitors we see are just flat screen everywhere. Those ones had Ogo. They were very big headed. That was around 1952, and this is with Univac. Now, software or programming, primitive programs were written in raw machine codes, and I told you that those machine codes were numbers, ones and zeros. Nowadays, we can program easily. I teach some of my students to program, and whilst I'm programming, there are lots of things. So I teach them to program and the like. Um, so programs were written in raw machine code numbers. Okay, so later moving to a symbolic notation called assembly language and then translated by assemblers. But first of all, how do we use to program is by ones and zeros, by ones and zeros. Okay, so now where we're going to continue from is the second generation. The second generation from 1954 down to 1962. That's the second generation. 1954 down to 1962. Okay, so core technology. Core technology. Let me bring this here. So please let us take note of the years 1954 to 1962. Let's take note of the years 1954 to 1962. All right, so this is for the second generation, and the key points under this um, is is not much. The key point under this is not much. The core technology of the second generation are the transistors. They had discrete diode and transistor technology. Okay, so what do I mean by diodes? D-I-O-D-E. They're actually things that you see in integrated circuits in the ICs, all right, used to transmit electronic signals. So they had discrete diodes and transistor technology, and they were replacing bulky heat generating vacuum tubes. So remember I told you that you see that IC you're seeing, the motherboard you're seeing, the things that are used to connect the motherboards are very big. Okay, very, very big. And they bring out heat. I told you before that they bring out heat and all that from the vacuum tubes. So now, due to integration, where they're able to, in the second generation, they were able to reduce all these things to just a motherboard plate. Okay, so a motherboard plate. That's the discrete diode and transistor technology and replacing bulky heat generating vacuum tubes. So this dramatically will increase speed and reliability. And so it only was able to increase speed to zero point 0.3 microseconds. That's what it just did. So this is where the application of integration in further mass comes in. Okay, so something that was big as large as a room, they reduced it. Something that was using vacuum tubes. Can you imagine? they reduced it to just IC motherboard. That's why when you open the CPU, those green things you see inside and connections and all that, they reduced it to that using diodes. Okay. Now, if you open your phone, you see just a plate and you see some connections there, diodes, thorough integration, thorough integration. All right. So, it's only increased the speed to approximately zero point 0.3 microseconds. Okay, and that was actually helpful and reliable, but it was still slow compared to what we have now. If you use second generation computers now, you will get frustrated, you will bust the head, you will throw the computer away, you will flush it inside the toilet if you can flush it. You will run because nah, nada. Ordinary, even our generation computers are annoying. Sometimes your phone will hang, and we're in the age where we don't want anything to hang. We just want it to be going fast, 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 fast. In fact, you go as my mind thinks. Just follow my thoughts. That's how you want the system to be operating. When your thought is this way, let the system just move fast. You don't want anything. Yeah, you're working on Isha. So under the second generation, the memory was replaced. So replace sequential macro delay lines instead of them using the normal macro delay, they used magnetic cores. All right, align random access to data. So it was in the second generation that they actually started with the memory of random access, the random access memory. And remember, what is random access memory used for? If I should ask that question, what is random access memory used for?
Is it RAM? Random access memory.
Yes, RAM, random access memory.
Okay. I think it is used for I think it's the main one working. uh, like is the one that is function. Wait first. Um ROM is for storing pictures, right?
Yeah, your normal
I want to,
stuff.
why the RAM is the one working the main, like the main work.
Yeah, yeah. I asked you a question, you threw the question back at me. See your scope. Yes, that's correct.
So I just wanted to be sure. I was not sure.
Okay. Yeah, random access memory is used for the operations of the computer, and that's why it's good when you're getting a phone. You should get a phone that have a good RAM space. Most people don't think about that. They only check colors. Oh, it's fine. I like it. Oh, wow. See the design. And they take it. They don't even check RAM space or ROM. They don't care about those things, especially girls. They'll just say, ah, it's a fine thing. Ah, your laptop. They will not check specs. They'll just, the laptop makes sense. Bro, check the specs. Okay, so now at least I know you guys will be checking specs. Right, Pearl? Right, Gift?
Yes.
Mhm. If you know to check specs before, now you check specs. The higher the RAM, the more you can operate, the more you can use more things on your system or on the phone. The higher the RAM, the more you can use more things on the phone. So, yeah, the higher the RAM, the more you can use more things. So, it was at this part instead of we using replace sequential macro delay, they use magnetic cores. So what they use for the RAM was magnetic cores for RAM. And then in your CPU, if you open the CPU casing, you can be able to remove your RAM and replace your RAM. That's how sweet it was. Then you just open your computer, You know where the RAM is. Remove the RAM disk. Go and fix another one there. Too sweet. Now everything is integrated. You know, everything is inbuilt, 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 sealed, integrated. Start looking for one technician somewhere. Oh, sweet Jesus. All right. The next thing is architecture. The architecture of the second generation. I want to talk about the architecture of the second generation, how this generation was being able to be flexible, operate from hardware to software. So the architecture of this is that the second generation introduced index registers. Please take note of that. Index, let me see. That is in page 16 of your unit 2 course. So index registers for controlling loops and floating point units. So there were two things in the architecture of the second generation. Index registers for controlling loops. Loops are like normal play pause operations, and floating point units to handle real number calculations in hardware, not just software. So that's what second generation they did. They introduced index registers and FPU, that's the floating point unit, to handle real number calculations in hardware, not just software. So when I say index registers for controlling loops, you go back and forth in your computer system. It was the index registers that are going to do it. You going back and forth, going back and forth, controlling your pulse play, controlling your continuation of a software or a particular software or where you stopped and all that. That's the index registers. Okay. Now we now have software languages. Okay, from high level programming languages like Fortran. Okay, so the software language, the software or languages were built from Fortran, Algol, and COBOL. Up to today, there are some people that will still ask you if you can write Fortran. Somebody that can code in Fortran, they were the ones that were able to create or build the new systems, like the IBM systems. Those systems, those days. Okay, those systems, those days, these were the people that were able to write with those codes. Those codes are very difficult. They are ones and zeros. Yeah, look, our code now is very easy. If you sit down properly, you'll be able to learn software engineering. You'll be able to learn Python. You learn JavaScript. You learn, I mean, children are learning it. You learn CSS. You learn, you learn various things. You learn GOS and the rest. You learn C sharp, C plus, C sharp, and the rest. You learn all those things. C, because you feel like, oh wow, it's easy if I just put in this inverted comma, I put in this colon, wow, wow, wow. Yes, but then the coding languages were just ones and zeros. 1001, 1100, 110, 11101. You've made a mistake. Go back. 11100. Guy, because the computer they were able to only read in ones and zeros. They were able to only interpret in ones and zeros. So you see the forefathers, those guys, they're the ones that have done the amazing work in ensuring that we have a foundation. Now we can just check our system. Now you can connect with me. Before it's only ones and zeros you'll be seeing on your screen. Anyways, so the software languages, emergence of high-level programming language like Fortran, which is 1956, Algol 1958, and COBOL 1959, and supercomputing in the second generation. Okay, second generation saw the first machines designed for numeric processing, like LARC, I told you about IBM, and IBM 730, introducing primitive forms of parallel processing. So it was in the second generation that most of the computers that were being produced were used for normal numeric processing, like your calculators. IBM was actually used for, they used IBM in NASA. NASA is the spacewalk where lots of mathematicians they worked in. So in the engineering department, they had to calculate or propel properly where their aviators or where their astronauts rather, where their astronauts are going to land on the moon or come back. So if their calculations are not right, it's going to cause a very big problem. An IBM machine was actually used. In fact, it was a black woman that started the initiation of it. I think her name is Jackson. I've forgotten her first name, but it's just Jackson. If you want to know more about it, just watch Hidden Figures by Taraji P. Henson. She's the one that acted that movie, and you'll know
I've
about
watched it before.
you, you know about the documentary of Hidden Figures. Okay, sorry, you were saying you just what dreamt about her.
I said I've watched it before, Eating Figures. I
Okay,
watched it.
yes, yes. So Hidden Figures. All right. So that's the IBM LAC. So that's their supercomputing for the second generation. Then we move over to the third generation, 1963 to 1972. 1963 to 1972. That's the third generation, 1963 to 1972. Now, the core technology that was made in the third generation were ICs, gang gang. So in the second generation, they were learning how to use magnetic cores. In the second generation, they were also learning how to use diodes and magnetic cores. Now in the third generation, the main ICs came out. ICs are integrated circuits. Gagaga. So now this is where they had a very huge achievement because damn, this was a very beautiful achievement because now you don't really need so much heat. You don't really need so much magnets. You don't need so much. They were able to integrate things and make it smaller and more portable, to be in homes, to be in homes. So core technology that was made in the third generation was the integrated circuit, semiconductor devices with multiple transistors on one chip. You see, just like when you open your phone, that green plate, or when you open the computer, that green plate, the motherboard. This is what we call the IC, a semiconductor device with multiple transistors on one chip. All right, so this started with small scale integration known as SSI and moved to MSI, medium scale integrated circuits. And trust me, they're the best. You will learn more about integration when you're dealing with in mathematics under integration. You will learn about it. You'll see why they solve differentiation and integration. You'll see why they solve it. And they use that integration. Integration, you can make something very big to work more powerful, transform it into something very small, but it will be more potent and more powerful. That's what integration can do. That's the power of integration. That's the power of that calculation that you didn't want to solve when you were in secondary school, that you were running away from. That integration. Yeah, yeah, that's the power. So that's the core technology. Now, let's break it down. The memory. Memories, semiconductor memories began replacing magnetic cores as the main memory. Remember, magnetic cores became the memory in the second generation, but in the third generation, they started using semiconductor memories. How was the architecture? Major emphasis on parallelism. It had multiple functional units, overlapping CPU and input and output operations. Okay, so um, okay, this might actually be a bit shaky, but let me explain. Now, the architecture or the way it ran or the way the operations were is that it was able to have various functional units, like do more things than the second generation. That's what it means. Overlapping CPU and I/O operations means that overlapping input and output operations. Okay, coming in and coming out, information that you're keying in and you're seeing your outputs immediately, and pipelining, internal parallelism. That means the things that work inside the computer system. Okay, so you can see the breakdown of the architecture that the CDC 6600 in 1964 was the first to use functional parallelism, okay, of 1M flops. And the CDC 7600 was considered the first vector processor of 10 MFLOPS. And then they introduced operating systems and time sharing. So, what I mean by that is the CDC 6600 in 1964 was the first to use functional parallelism. When we say functional parallelism, we mean how the system operates, how the system carries its functionalities. Can the system do five things at once? Can it do 10 things at once? This was running at 1 M flops, meaning that the amount of space or the amount of speed it was running at was 1 M flops. But the CDC 7600 was considered the first vector processor, and it was running at 10 M flops. So 6600 and 66 and 7600, there was a wide difference. There was a wide margin. And we can see that one was 10 times faster than the other. And after that, they just introduced OS, operating system, system software, OS. You know, OS was then introduced and time sharing. Operating systems were then introduced in the third generation. Please take note that operating system came out in the third generation. Third generation spanned across 1963 to 1972. And the core technology that was made in the third generation were integrated circuits. This was a big leap in the computer industry. A big leap in the computer industry. Okay, called the integrated circuit. Um, Remember that the integrated circuits were based on a small scale integration, which can have around 10 devices per circuit or chip, and then it moved to medium scale circuits, which can have 100 devices per chip. That's how it is. So when we talk about overlapping I/O operations, pipelining, internal parallelism would mean the internal functions, how these things operate and how they carry out their operations, various operations. Um, okay, let me see, let me see, let me see. Okay, and then they had the introduction of operating system in the third generation, and the software languages that were created then were development of CPL and the subset of BCPL. Those were programming language. Just no need to go deeper because these are into software engineering. Just know what the software languages were during the third generation. I told you that during the second generation, the software languages were Fortran, Algol, and COBOL. During the third generation, we had the CPL and BCPL, and those languages that came out were still using ones and zeros, a little bit of ones and zeros. Okay. Now the fourth generation. The fourth generation. Now the fourth generation, 1972 to 1984. That's the fourth generation, 1972 to 1984. Now you might be asking what um, CPL is, or probably all these things. CPL is called Computer Programming Language, and BCPL is called Basic Computer Programming Language. So, in fact, could even be could be mm, take note of the architectural systems in each of the generations. And when I say 1M flops, we mean flops is like floating points, okay, floating point operations per second. That's the meaning of flops, how fast these things are able to operate. So don't get confused with that 1M flops and the likes and 10M flops. But you know that 76, CDC 7600 was way better than CDC 6600. All right, now in the fourth generation, the core technology they were able to do is the large scale integration, which was able to take in over 1,000 devices or chip on a single plate. Very large scale integration, the LSI and the VLSI. And now the VLSI was able to take 100,000 devices or chip on a single plate. So let me just let you know that when you hold your motherboard or when you hold that integrated circuit, when you open your phone, and I'm sure probably if you open the phone before, you see all those green things that are inside the phone and all that. That's the chip. That's the integrated circuit. That's the chip. That's the integrated circuit. Okay. That's the chip. That's the integrated circuit. So, um, now the LSI, you see so many things that are being attached to it. Those things are the devices, okay? Devices that are being put on the chip. Devices that are being put on the chip. Chimo. Yeah. Devices that are being put on the chip. And for the fourth generation, they had a lot. They were able to integrate a lot of things on just one chip, allowing entire processors to fit onto a single chip, known as microprocessors. So if you check it, you see different connections are coming from different places, but they connected all the whole circuit on one plate, forming a better computer system. Then they gave it one processor, a microprocessor, a chip that was able to control or that's able to control all the processing units or all whatever is going on that same plate. Now, this thing just looks like witchcraft because somehow you'll be wondering if technology is not witchcraft because how are they able to discover those chips and how were they able to do it? That's the chip. And how were they able to do it? Able to it's amazing actually. When I sometimes I try to understand how they discovered it and then how they integrated it and I'm like, ah, this thing must have been witchcraft or this thing because where are you getting the inspiration from? Spirits must have taught these people how to do these things. No, 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 you can't tell me. All right, so the semiconductor memories fully replaced core memories as the main storage. So, just like the third generation, they now use semiconductor memories to replace core memories as the main storage. And the architecture in the fourth generation is that it was dominated by high-speed vector processors. Now, the processors that you guys might have, you check your phone pack, you see the processors that you have. If you check your phone pack, you see the processors that you have. So as of the fourth generation, they were vector processors, like the Cray 1, the Cray XMP, and then they started the emergence of microcomputers and workstations as alternatives to mainframes. So the microcomputers are like the ones we could put in our homes. That's the fourth generation. This was around 1972 to 1984. I'm sure some of your parents already bought those ones in their homes, or their dad or your grandparents already bought some in their homes. That time, not every home could have one. That time, not everyone could have one computer in the home, so it was quite very expensive. Okay, okay. So Now, mm, the architecture is of the fourth generation is that vector processors were out, emergence of microcomputers and workstations, as well as alternatives to mainframe. Now, software languages that came out in the fourth generation, C. I don't know if you know about programming language C, but it's actually a very good programming language. They use C sharp to make your bank apps or the bank application apps that you guys use now. It's C sharp that they use to design it. So C came out in 1972. That's the C programming language. And the Unix operating system, just like your Linux, is actually a very good um, operating system to code. That one was also written in C. And there was also VHLL, that's a very high level languages like FP and Prolog using a declarative style. I don't know about FP and Prolog. I've never checked those languages before, but there are many languages. Languages, don't worry, there are plenty. Ide, okay? And let me see. And for the fifth generation, so the operating system that came out in the fourth generation was the Unix operating system. And for the fifth generation, and for the fifth generation, the core technology or the things that they made was the continuation of the VLSI. Remember what the VLSI is? VLSI is actually a very large scale integration that was able to take in 100,000 devices on a single chip, allowing processors, single microprocessors to sit down. That's like your CPU. They will put in processors to sit down on that same single plate. And up to now, I still need to know how they do those things. You know how they do those things. Because just like when we found out the discovery of the um, technology, a man keeps water, a very tiny scale of water, beside a tank, and he said he uses resonance frequency. And the water in the other tank, very small water, like let's just say you're keeping a tiny amount of water beside a tank. The water in the tank will get purified because of the one that is beside it, saying it's using resonance frequency. And you tell me that's technology? That's witchcraft. There are some things I'll just be like, no, there's no way, there's no physical explanation to this except juju, witchcraft, pure one, jazz. What are you telling me? All right, so for the fifth generation,
That one possible. How can they do that?
yeah, this was 20, this was 2017 or 2018. He collected Nobel Peace Prize in physics. He said the water uses resonance frequency. His family has been working on it. If you look at the man, Seth, he looks like a wizard. He has long white beards. You just know these people are doing witchcraft. They call it technology. Okay, when I started researching or checking these computers and generation, I cannot just phantom how they got the processor, made the processor and pin it down on top of a plate. How? Eh, Well, anyways, let's just know that the fifth generation, how are they even getting the programming languages and all? Guy, these things are just, to me, all I can say is some part of science is witchcraft. Fifth generation, 1984 to 1990. And the core technology in this was the continuation of the VLSI, that's the very large scale integration, leading to chips with millions of components. Semiconductor memories became standard on all computers. What was the architecture of the fifth generation? They had widespread of parallel processing, including machines with hundreds of processors working on a single program. Okay, There was shared memory and distributed memory models. So the architecture was parallel processing, not your previous processing. What's the name of that other functional parallelism? No, not that. This was parallel processing because they had a lot of VLSI. VLSI means that instead of you, um, one VLSI is like 100,000 chip, 100,000 devices on a single chip, okay, with microprocessors on it. Now, multiple VLSI will be millions of devices on chips with semiconductor memories. And those semiconductor memories are the RAM on which they're going to operate. So the architecture models, they had distributory models which were commercialized, data parallel, single instruction, multiple data machines appeared like connection machines. The fifth generation was just so cool. This was around the time that some of us were giving birth to, 1984 to 1990. So, you know, it's like that was that was the computer of the day then. Yay. Networking, the networking was the wide area network came out, the local area network came out. But these things were using wiring. So it was driving a transition towards distributed computing environment using single user workstation. When we say single user workstation, we mean I can be in my home and connect to somebody somewhere else. Okay, so single user workstation, and this technology gained prominence. So there are just a lot. There's a lot of information. Let me see, let me see, let me see. Yes, risk technology gained prominence. Okay, so in this part, scientific computing in this period were dominated by vector processing. Yeah, we talked about vector processing in the last one. Like in the fourth generation, remember vector processing, high speed vector processors like Cray 1 and Cray XMP. All right. Uh, so right now we have multiple processors these days. So yeah. So in the fifth generation, they also had um, they were dominated by vector processing, and most manufacturers of the vector processors introduced parallel models. Okay, they use parallel models in parallel machines. Meaning, when I say parallel models in parallel machines, we can be doing almost same thing at the same time. You can be running almost multiple programs at the same time. But it was still very slow at least. It was still a bit slow, but not so slow as the second generation or the third generation. You get the first is nothing to write home about. Don't even go to the first. Okay. So it was still a bit slow. And in the fifth generation, we now had wide area network, we had local area network, you know, and computing environment. When we say distributed computing environment, we mean that user friendly. I can be in my home, you can be in your home, and we can connect, we can talk. When we had a WAN, especially, we can connect and talk. Now, the sixth generation is from 1990 to date, and what they created in the sixth generation, the core technology, was massively parallel architectures, all right, to achieve teraflops. When I say teraflops, you should understand what that means. That's like 10 billion operations per second. Before we're talking about million flops, M flops, 10 M flops. Those ones they are just little. But now in the sixth generation, we're talking of teraflops. So we have like 10 billion operations per second. Performance using thousands of processors. I say professor. Oh Jesus, thousands of processors at the same time. Like you're listening to music, you're typing here, you're doing this. As I'm doing this, I can be listening to music and recording, and there are multiple things running with good speed. Now that's what we're talking about. That's sixth generation. hmm Hmm. Don't get me no system that hangs. I can flush it in the toilet. Hmm. That's what we're talking about. So, or throw it in the lagoon. Imagine you buy iPhone 15, and then your iPhone is hanging. What will you do? You throw it away now.
Exactly.
You
But
flush.
instead of throwing it away, I will sell it to any amount you give me. But instead of throwing it away, because it's more nice than iPhone.
Eh, no, like you just be angry and throw it inside that lagoon in Unilag,
Hazard now, this kind of somebody can never be as angry about Hazard to your phone, iPhone. iPhone, no, iPhone, last way.
Ah,
Not possible.
I've seen angry people like that too. I don't know if it's iPhone.
iPhone,
I think it's Android. It's true.
ah, better. It can never be iPhone. You not even mention 50. It can never be iPhone. Person that is using iPhone 6 don't save. If you know the way they are, like they are taking care of the iPhone 6, talk less of iPhone. What I don't know that they are using that.
Anyways, it's still just a phone. Those things don't even have value than some real Android. Android users are the main markets, Jerry. Architecture. Paras,
Yes.
Paras systems began to dominate supercomputing. Workstations combined risk pipelining and parallel processing, achieving the power of previous generation supercomputers. And this spurred to what we call the heterogeneous computing using idle network workstations for parallel subtasks. So I can be here and use my own network. And the networking dramatic growth in network bandwidth. When we say, talk about network bandwidth, how fast we're able to communicate. If I have a low bandwidth, it means that I'll not be able to pass information across to you guys that are over there. I'll only be able to grab, like, you will not be able to hear me properly. So if my bandwidth should go low, I'll start cracking. Do you get? So in the sixth generation, sometimes if the network is affected, my bandwidth might drop and I'll start cracking. Or sometimes Pearl, you say you don't hear gifts, so our bandwidth might be dropping and you'll not be able to hear from your own end. Do you understand? So that's how it is.
Yeah.
So the now in the sixth generation, there was dramatic growth in the network bandwidth from T1 to T3. It was making wide area networks and local area networks widespread beyond universities to education, private industry, and boom, that's what we have to date. So, this is a whole lot of information. I'm telling you that your unit 2 for your computing that talked about this first generation, second generation, I still feel like I even want to go back, study more, and fish out more things. If there are other things I was not able to fish out, let me see, because this thing starts from page 11 down to page 25, so you can understand how it is almost 14 pages for just one unit. Kilo day. So you should know what's up. The unit 2 actually, and in your TME, damn. We're just receiving from left, right, receiving various, you know, things they were asking us about bandwidth teraflops. If you guys did your TMA, you understand what I'm saying now. Okay, 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 okay. Now, that's it under the sixth generation. Now, to some of you, okay, to some of you, what I've been saying so far might just be yan, 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 yan. Maybe I was just backing or something. So, please, are we here? Gifts, are you in class?
Yes, I'm in class.
Oh, so that you stayed quiet like this. Hey,
This just 103 load.
the load is too much, Abby. Even after I
Really
tried to,
form of like a confused day.
even after I tried to bring out points, the thing is still well loaded.
This site of growing up
Thing is still well loaded, and
is as if it's the hardest course. I don't even know.
yeah, yeah, something like that. It is because the first TME, it was this is the first one I was doing TME for this course, and I got 6/10, and I was like, what?
Mhm.
And I was like, no, no,
More
no.
experience.
I had to go back again. And when I did the TME 2 and I got 8, I was like, TME 3, I think I got 7 back. I just give up that no, I beg. I was just like, I beg, I beg. So, what was I even doing that TME for? All right, so there are questions here. Mm, okay, okay, so there are questions here. And these questions, we're going to tackle these questions because uh, questions look very, very funny. All gotten from these parts. And it will just enable us to touch more on the document. Let me see. All right. So let's do it. So I'm going to give you guys a question. I'll drop the question and we tackle those questions because we need to be understanding this in depth. No excuse. Let me see. Let me see. Chai, your phone is very low. Can you imagine? Eh? Can you imagine? All right.
Yes, I will soon leave now. My phone is at 5%, so I'm going to cut it now. All right. Good night, everyone. Bye bye.
Cha. Bye bye. Next time, charge your phone now.
Come on. This
All right. So we're just the only two left. Okay. So let's tackle.
better.
Let's tackle it then. All right. So first question. First question says, explain the significance of the stored program concept in the evolution of computers, specifying which first generation machine introduced this idea. They said stored program concepts. Just think of EDVAC when they talk about anything storage. Think of EDVAC.
Okay.
Yes, so stored program concepts. That is going to be EDVAC. Now they said we should explain the significance. All right, so now the stored program concept is the fundamental principle of that both program and instruction and the data they operate on can be stored in the computer's main memory. And this idea was introduced by EDVAC project. EDVAC is Electronic Discrete Variable Automatic Computer. Okay, so um,
Okay.
prior to this EDVAC, computers like the ENIAC were programmed by physically altering, switches and cables, like those vacuum tubes and all that. So you have to be using switches, using cables, using switches, using cables. So um, prior to the concept like that, computers like the ENIAC, as the ENIAC, they were programmed by physically altering external switches and cables, and it's limited processing speed and made programming extremely time consuming. So this storage part that came out from EDVAC is just the beginning of storage. By storing the instructions in the same high-speed electronic memory as the data, the program could be executed. That means if we store it, even if we store little by little, if we store it, we can execute the program. The program can be executed. We can modify rapidly by the machine itself. So the single concept is what made the computer a general purpose machine rather than just a specialized computer calculator. So, and this now led to the massive growth of creating memory in other generations. So the EDVAC was that project. Okay, and um, prior to the project, computers like ENIAC were programmed using switches and cables before they now brought about EDVAC. Okay, let's use EDVAC to be storing memory, because if we store memory, we can be able to continue what we were programming, and it will make it a little bit faster than just using switches and external cables all the time and coming back to square one and starting all over again if this thing should blow up. So um that's that's an explanation of the significance of stored program concept in the evolution of computers. You know what, let me even type what I said. One second. Please, let's invest in solar. Oh. Actually, I use solar at the office. So uh anyways, I'm not usually out of light most times. I'm not usually out of light most times. Okay, so the answer to the first question, question one. Okay, so I'm going to type that here, and I'll type in my explanation as well to that. So you can just use that to compare. Probably if you have yours, you can use it to compare what yours is, you know, and see how it is. Okay, so one second. Okay, so for the question one, and remember it says explain the significance of the stored program concept in the evolution of computers, specifying which first generation machine introduced this idea. Okay, now, second question. The second question says, describe the major technological shift that defines the transition from the first generation to the second generation of computers, and state the impact this change had on two computer characteristics. How did yeah that's actually tough. Okay, now the the major technological shifts was the replacement of vacuum tubes because the first generation used vacuum tubes. So in the second generation, they used transistors. So the major
Yes.
technological shift was the replacement of vacuum tubes with transistors as the primarily electronic switching component. Now, in the first generation, they used the switching component of vacuum tubes and external switches and cables. Boring. Second generation, they started using transistors, okay, as their main electronic switching component. So the technological shift is vacuum tubes were very large, they are fragile, they can generate massive heats, you get, and they consume vast amounts of power. And sometimes they fail because they can run out. Transistors invented were more durable. They consumed minimal power and switched thousands of times faster. So let's say, inside the IC, there are lots of information that we're trying to process in the computer, that the computer is sending signals to other parts of the system to run this, run that, run this, run that. If the signals get stuck in the RAM, then the computer will what hang because there's not enough space for that operation to continue. Then the computer definitely will have to hang. Do you understand? So now, for the first generation, okay, for the first, let me see. So now, for the first generation, all right, for the first generation, um, they used the vacuum tubes, and it was so because in order for you to let's transfer this information to the other information, they will have to switch, use external switches, plug it from here to here, plug it from here to here, and that thing was generating a lot of heat, and it can blow up at any time. So the thing is, the technological shift was the transistors, and and mm, let's see, let's say um okay, another thing was let's say they said impact on characteristics. So what can I say here? For the impact on characteristics, let's talk about the size and heat. Computers became significantly smaller and generated much less heat, making them cheaper to house and maintain. The speed, switching time dropped drastically to zero point 0.3 microseconds. Remember when we're talking about that, making
Yes.
processing
Yes.
faster. And then we also have reliability. The lack of moving parts and reduced heats increased machine reliability and lifespan. So instead of you moving and switching like the vacuum tubes, the transistors will just be doing that work, which made zero point 0.3 microseconds faster. So, yeah, that should be it from your course. Are there any other thing? No, now they just said two characteristics. I beg. Yeah, that's it.
Next one.
The next one. Hey, see the way she said the next one. Okay. All right.
Wait, oh, but where is this? Where is this GS 103 so?
He said, why is what?
Why is GS 103 hard?
It's because you're talking about system. It's not really meant to be. It's not really hard. It's just this history part that is a bit crazy. And you now you be thinking that, okay, you're talking about old things, digital, computer, analog, hybrid. You're talking about old things. So you now you be thinking that, oh, yes, so I know how to use the system and all that. But the kind of things that they're talking about in this course is the like old computers, old things, how they became what they are now. And they want you guys to have computer knowledge.
Okay.
I want you guys to have computer knowledge. The third question says we should discuss the role of ICs in the third generation of computers. What key architectural innovation related to parallelism emerged during this era? Ah, okay. Discuss the role of integrated. Okay, now integrated cycles combined multiple transistors. You know, in the second generation, they use transistors instead of vacuum tubes. Yeah. Now, integrated circuit
Mm.
now combined multiple transistors and electronic components onto one single chip. Remember, we talked about the SSI and the MSI onto one single
Yes.
chip. So they made it onto into one single chip. Now, the key innovation related to parallelism was pipelining and the use of multiple functional units. Pipelining and the use of multiple functional units like the CDC 6600 and CDC 7600. So now let's talk about the role of the IC. They said we should discuss the role of the IC in the third generation computers. Okay, let's talk about the role of the IC. Um, by reducing or integrating all these things into ICs, designers achieved, huge gains in performance and density because now it's going to reduce cost, it will increase speed, and it will pave the way for more complex internal architectures like the use of semiconductor memories to replace magnetic cores. Then in the second generation and third generation, they use magnetic cores as their memory. In the third generation, rather, they introduced semiconductor memories to replace the magnetic cores they use in the second generation, making it more faster, making the space more bigger. Okay, so the role of the ICs, they integrated all those large headed things into a single plate, a single chip, making it more portable, faster, durable, reliable, you know, and the architectural innovation. The third generation introduced techniques to execute various instructions simultaneously. Pipelining, what pipelining does, pipelining breaks down instruction execution into stages. It allows new instruction to begin before the previous one is finished. That's what pipelining does. Now, the use of multiple functional units like the CDC 6600 meant that different parts of a calculation, like let's say the arithmetic and logic, could be handled independently and in parallel. So it is boosting the computation rates of M flops. The thing about the CDC 6600 for the multiple functional units is that they run in M flops, not teraflops. Teraflops are billions. They run in M flops, not teraflops. So that's the use of multiple functional units. So pipelining breaks down instruction execution into stages, allowing new instructions to begin before the previous one is finished. Let me just say, pipelining allows multitasking, minimizing, and I can minimize what we're doing now, open another thing, open another thing. That's pipelining. Okay, now the use of multiple functional units will apply parallel, um, uh, it will also apply parallelism. Okay, so different parts of calculations. For the multiple functional units, it can be operating different parts of calculations independently. So the rate at which the operations or the frequency of the operations is being carried out, the millions of the frequency of operations being carried out, that's what we call the envelopes. So the real answer is integrated circuits combined multiple transistors and electronic components into one chip, starting with the SSI, which migrated to the MSI. And the key architectural innovation related to parallelism was pipelining and the use of multiple functional units. That's then if someone wants to discuss, person can go and be discussing. Because no, I just finished discussing, but I beg. Yeah, yeah. So next question.
Number 4.
No more. This thing requires water. See? Jesus. Next question. All right.
Okay.
Okay, when you're ready.
Number
When you're ready.
already.
You're ready so fast.
Eh,
Be,
me already.
uh, be calming down. Oh. Okay. Um, the fourth generation. It says identify the core technology of the fourth generation. The fourth question. Identify the core technology of the fourth generation of computers. Explain how it contributed to the emergence of both microcomputers and workstations. Okay. Mm. All right. So the core technology was VLSI. Remember what VLSI is? Very large scale integration, which led to the creation of microprocessor, a complete CPU on a single chip. That fourth generation, a complete CPU on a single chip. Did they associate explain?
No, I didn't know. I didn't also
Oh, he said explain how it contributed to the emergence
identify.
of
Okay,
both.
yes, yes. Okay,
Okay, so now for the fourth generation, well, this one is quite easy. VLSI and micro, VLSI and hello, can you hear me? VLSI and micro um, processor. Now, the VLSI allowed the integration of hundreds of thousands of components onto one single chip. Now, this breakthrough meant that CPUs that used to fill an entire room or cabinet could be manufactured on a single low-cost integrated circuit, which is known as the microprocessor. The emergence of microcomputers and workstations. So, because they were able to integrate these things, all right, into one chip, hundreds of thousands of components into a single chip. Remember, I told you about VLSI. Now, the emergence of microcomputers and workstations became um, possible. The affordability of the compact size of the microprocessor made the creation of microcomputers, which is known as personal computers or PC, possible for the first time. So, simultaneously, more powerful, high performance microprocessors led to the development of workstations which like it's providing individual users with dedicated computing power, rivaling the earlier mainframe computers that are big-headed that could fill the entire room, moving away from centralized time shared computing. So time shared computing, you have to leave the room, another person have to enter. That was just time shared computing, rubbish. But you see, the emergence of the VLSI and was able to make the microprocessor. That means you can take the entire CPU, integrate it, and put it on a single chip. And because of this, we started making what? Personal computers. So that's the core technology of the fourth generation. And that's how it contributed to the emergence of both microcomputers and workstations.
okay. Next question.
This question has our gift. Jesus.
What should we take a break, sir?
You see?
We should go on break, sir. We continue. We postpone it to our next class.
No, 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 finish. Next question says name two
Okay.
high. Sorry.
Mm, Then,
Okay, what were you saying? I didn't hear you previously.
yeah, I said I want others to also partake in this question because this question is, I want them to have idea about it. Yeah, because these questions are hard.
Okay. But it's mainly telling us to explain and all right, I get it. But in when they come in for the
So
next
that I can just,
class,
mm,
when they, am I going to? Uh, anyway, this was recorded, so I'll just tell them to go and watch it.
you can just, in our next class, you can just like, just start from this question, like just a little revision on the question,
Okay.
like this question.